Okay, it's 7:20 by my clock, so this will be the beginning of first lecture for mae42431 Aerospace Propulsion. Okay, this lecture is going to begin a series of lectures on turbo machinery, which is the heart of a gas turbine engine, both for aircraft, for ground power systems, and for things that require shaft work or produce thrust. What we're going to start with is just a general overview of mechanical compression systems that are in these devices, namely compressors and fans, and we'll devolve into the design of axial flow fans. Briefly, we'll mention centrifugal compressors, but we will not spend much time on that. So I'm going to now switch to a set of PowerPoint slides that we will go through. So let's begin speaking about fans and compressors, and specifically axial flow compressors. And let's begin by talking about what their primary function is. The primary function of the compression system, the mechanical compression system, is to raise the enthalpy of the working fluid in one of these engines. And we're talking about an air-breathing engine right now. So how does it do that? Well, a series of rotating blades raise the pressure, and at the same time it raises the temperature of the working fluid, and raises the enthalpy to a point at which you can inject fuel, raise the enthalpy even more, and then extract either useful work through shaft power or convert to kinetic energy for thrust. One of the distinguishing features about compressors and fans are that they operate under an adverse pressure gradient. We've mentioned this earlier. We talked about inlets and diffusers. And so the concept of aerodynamic separation is always on the mind of a compressor designer, because he's always dealing with flows with an adverse pressure gradient that tend to separate boundary layers, which just then tend to disturb the gross flow in general. So this is something that is always in the back of the minds, and it actually limits the amount of work that a compressor can do for a particular stage. The flow field in turbo machinery, not just compressors but also in turbines, is extremely complex. What you're seeing here is a kind of a cartoon of what types of flow fields, what the flow field looks like in an axial flow. In this case, compressor, could be a turbine. When we get to talking about turbines, there'll be slight modifications, but a lot of the same features exist. You have flow that's moving through channels. It's a guided turning, okay, because you have airfoils that are close together, and that creates a channel. But you have these channels that are made up of airfoils. And what we know about airfoils, just like you've learned before in your aerodynamic classes, is that there's low pressure sides and there's high pressure sides. And so the flow, as it moves axially through the passage, in the lower momentum regions near the boundary layers, near both the blades, the bottom surface, which we call the casing, we call the hub, and then the top part, which we'll call the casing. In these low momentum regions, they can become susceptible to these different forces, these pressure forces. So you get flows that creep up along radially, mix with the boundary layer on the top. You get tip vortices, just like you do on a wing, a fixed wing. Okay, well, each one of these is an airfoil, and there has to be a gap between the top and the casing surface. So there's going to be what we call our tip vortex. And so these boundary layers and these lower momentum flows all interact, and all of these add up to be losses, okay? And they can be very complex flows to analyze as well. Adding to that, if you have speeds that are sonic or supersonic, which are certainly possible and are definitely present on fans and certain compressors, a portion of the blade could be supersonic flow. Thus, I'm going to have shock surfaces. These shocks attach to the leading edge of each of these blades, and then they come and they can impinge on a blade that's next to it. Okay, and we discussed the other day of how shock waves interact with boundary layers, and it's not good. You've already got an adverse pressure gradient in here to begin with. Shock impingement on surfaces just add to the problem. You can have unsteady flow through this machine. You can have flows that are very radially. You can have flows that vary circumferentially. So this is a very messy flow field, but a lot of progress has been made in the last 40 years on analyzing this problem. And so we've gotten the adiabatic efficiencies of axial flow compressors in the low 90s. Okay, so a typical modern designed axial flow compressor adiabatic efficiency is going to be in the area of 0.93, maybe even 0.94 if they're really good. Okay, so low 90s adiabatic efficiency. To go that extra step to get, say, 98% would require a very lot more work. So we're on the kind of asymptotic part of that efficiency curve. So complicated flow features, and what you're going to need to start getting used to, and you'll get used to as we do some problems and you do homework problems, is, and we'll talk about this in detail later, being able to go to change reference systems. Okay, we have a rotating reference system here. Okay, it's a rotating. These blades are rotating. They pass flow onto another set of airfoils that don't rotate. Okay, and so when we analyze that flow field, we're in a different reference system. So we're going to be hopping from on a rotating reference system to a stationary reference system and back and forth. Okay, and so we have to kind of keep that straight. And the way that we will distinguish between these two reference systems will be, one is the absolute reference system, the stationary reference system, and then the relative frame of reference will be the flow on the rotating surface. So this just repeats some of the things I said. The axial flow compressor is complex because it's close to the proximity of the rotating blades, buildup of boundary layer, presence of leakage. What this means is that as flow gets near the tip of each one of the blades, just like on a fixed wing, the flow from the bottom surface wants to crawl up and go on the upper surface. It leaks around that clearance that it needs so it can rotate. So in order to get a very efficient compressor, axial flow compressor, you want to minimize that clearance. Okay, and then of course the secondary flows. You're going to have secondary flows no matter what. What are secondary flows? These are those flows that are not going axial through the machine. They're the ones that are moving up and down the blades, across, in directions that are tangential and radial. Those are considered secondary flows. Okay, so assessment of these loss mechanisms suggests that approximately half of the total loss in the rear stages of a multi-stage compressor is associated with the end wall boundary layer. So you also have growing boundary layers through this. And as we'll see with the typical flow path, as you're increasing the pressure and increasing the density, the flow path is actually getting smaller. So the blades are getting smaller. So the relative distance between the hub and the casing gets smaller and smaller, but the boundary layer is filling up that passage more and more. And so that's where a lot of the losses occur. And this next bullet will explore more. There's a trend to going to low aspect ratio compressor blades, and not necessarily fan blades, but compressor blades. And this increases the fraction of total flow subjected to the 3D and end wall boundary effects. Okay, so to repeat, the trend, and I'll show pictures of this in a moment. If you looked at an axial compressor from, say, the 50s, the aspect ratio of the blades would be relatively high compared to what you would see in a modern axial flow compressor. And there's a very specific reason why that happens. But one of the consequences of that, in other words, that was done for a reason. We'll get to that later. But the consequence of doing that is that you increase these end wall boundary layer effects. So it actually, you start to battle this efficiency loss due to secondary flows when you go to small or low aspect ratio flows. So therefore, it's important to find ways to reduce these losses. We want adequate stall margin and high efficiency. That's the goal. That's the holy grail for a compressor designer. Stall margin, we'll define it specifically later, but in general, what that means is that all these compressors have a point at which all the flow can actually reverse itself and actually move forward through the inlet because of extremely high pressure, back pressure. Okay, we call that stalling. Stalling of a particular blade leads to stalling of several blades, leads to stalling of the whole annulus, and the engine essentially burps flow out through the front. Okay, that can be catastrophic. In either case, it'll cause the engine to malfunction. Okay, so you want to be able to run and operate in all the operating conditions of the compressor sufficiently away from that point. All compressors have that point. Okay, and when you design an axial flow compressor, your first job is to figure out what are those operating conditions in which that occurs. You will test the engine to the point or the compressor to the point where you find out what that is, and then once you know where that is, you back off, and then that distance between where that is and where you operate is something we call stall margin. But you want to be able to do that with high efficiency. So this puts a premium on the aerodynamic design for axial compressors, and one of the benefits of all of the work that's been done on CFD with the advent of faster and faster computers is that these complex three-dimensional flow fields can now be analyzed with three-dimensional Navier-Stokes solvers, both unsteady, and they've been very, very helpful. They're now, they used to be brought in early on just as a way to check a design that was done in a quasi-3D sense with two-dimensional analysis. And now I think most engine companies have a very strong part of their design loop is using 3D CFD to design the passages and the actual blade shapes. Here's some pictures of some types of flow field. Actually, this is a turbine blade here, but you can see that you have shocks due to supersonic flows in some cases. Here's some flow visualization of what happens when you have boundary layer separation. Okay, so these are all loss sources that you can have in compressors. This is a turbine blade, but it also indicates the presence of shocks. When we talk about turbines, turbine aerodynamics, this will be a key feature. But even in fans and compressors near the tip at supersonic velocities, you can have these shock waves that are very, very lossy, and they interact with the wakes and the flow from the adjacent blades. Just to give you an example of the early jet engine, this is the GE J31, which was essentially a copy of Whittle's engine that was developed in England. So essentially, GE bought the licensing from Whittle for this engine, and then they built the first U.S. or American jet engine in Lynn, Massachusetts. I believe it was the early 40s or late 40s. And what you can see here is that there's no axial compressor here. They have an axial turbine, but they have a dual centrifugal compressor. So flow will come in through here, through these veins. This is the entrance of the centrifugal compressor. The flow gets slung upwards and then into a combustion chamber here, burnt, all the enthalpies at its highest point right here, and then all of the work, or most of the work, will be the work to drive this compressor will be extracted from this axial turbine and then converted to kinetic energy through the the nozzle here. So it's compact. You see there are very discrete burners here, so there's I don't know how many there are, but there's at least 8 of these burner cans around the engine here. And what you see with the centrifugal compressor is that it has a relatively high diameter. It has pressure ratios that are over 2 generally. So for one stage of centrifugal compressor, you have fairly high pressure ratio. Here's just a picture that you can see more details. They're basically the kind of impellers you see on a supercharger if you've seen one of those before. So flow comes in again, gets kind of bites by the flow, the blades at this point. Flows get slung up centrifugally, and so you get very, very high pressure ratio for one of these stages here. Okay, but here's an example of a modern wide chord axial fan for a typical high bypass turbofan. This is circa like 1979. This is somewhat maybe in the 80s. This is the GE90 fan that we talked about before. You know, one of the biggest differences you'll see between modern ones, you'll see much more aerodynamic shaping that's done to get the highest efficiency of these fans. And this is a result of using those 3-dimensional CFD, whereas back earlier when we didn't have that, we had very rudimentary aerodynamic blades. Just to, again, get you familiar with what some of the part pieces are, this is an exploded view of a conventional high bypass mechanical compression system. Okay, so what are the constituent parts here? High bypass 2-spool, so it's a GE or a Pratt type of a bypass engine. The core compressor here, 9, this is a multi-stage high-pressure compressor, axial flow compressor. And these pieces here are the stator casings that come and put the stator blades in between these rows. So this is connected to a shaft. It's connected to the high-pressure turbine. Okay. There's a shaft that goes through the center of this spool that's connected to the low-pressure turbine, and that shaft connects to these rows of blades here that are called the booster compressor. Okay, and that's connected to the fan. So the fan blades 2. The booster blades here at 5 are on the same shaft and turn at the same RPM, which is different than the RPM of the axial high-pressure compressor. Okay. Again, the stators are in these cases that come in as a clamshell and just fit in between the rotating blades. This just gives you an idea of the mechanical assembly of the system. So what are some of the trends in compressor design in the last 50, 60 years? Well, there's been higher speeds. Okay, one way to get more work put into the flow is to have your compressor or fan, or think propeller, right, is to increase the RPM, increase the amount of work that it's putting into the flow, so higher speeds. Higher pressure ratios for a spool. Okay, a spool would be that high pressure spool or that low pressure spool. Okay, so just in general, the pressure ratio from the beginning to the end of that whole multi-stage system has gotten higher and higher. Each individual stage has increased its pressure rise capability. So even though it's an adverse pressure gradient, we've done a much better job aerodynamically in designing blades that can withstand that and give the nice pressure rise. This is in order to do this, that necessarily entails higher aerodynamic loading. Now, in turbo machinery, the term loading is used all the time. Okay, and all it means, the way you should think of loading is lift. Okay, it's just a lift that's on these blades, just like you would think of lift on a fixed wing aircraft. Okay, lower aspect ratio is a trend. So it's gone from high to low in the last 50, 60 years. Right now, the average aspect ratio for a compressor is about 1.4. Higher solidities, we'll define that specifically, but essentially what that means is it's a ratio of the chord to the spacing between each blade. Okay, so think about something with that has low solidity would let more light pass through it. Okay, an annulus of these blades. Something with high solidity would be more solid. It would let less light go through it. So the trend has been to move from low solidity to high solidity. Again, there's a reason for that. We'll talk about that later. And of course, improved configuration and blade shapes really relates back to higher aerodynamic loading, because this is a consequence of being able to do a better job aerodynamically. Okay, so here's a 25-year span. You know, this on the bottom here is like 1979. This compressor at the top here is designed in the 50s. Okay, so what you have is a comparison of the pressure ratio for this spool, high pressure compressor, the tip speed, and the number of stages. Okay, so you can see some very discernible trends. If you look at the pressure ratio, while these are relatively close, you know, 12.5, 13, 12, look at the difference in number of stages. So the CFM56, designed in the mid-70s, okay, was able to get a pressure ratio of 12 in 9 stages, whereas the CJ805, which actually, that's the commercial version of the J79, I believe, which is what was on the F4 aircraft, had about the same pressure ratio. It took it 17 stages. Okay, that's a huge difference. That's a lot of weight. And also, again, look at the difference in tip speed, right? 1300 versus 955. Okay, that means that we've improved our materials and able to handle that mechanical stress. Now, this energy efficient engine, this core compressor, the high pressure compressor for the this was an experimental engine that was built with funding from NASA in the late 70s, and it was a way to make can you make the most efficient commercial engine? This was during the oil crisis of the late 70s, and this was designed by GE. It had a pressure ratio across this spool of 23, and it did it in 10 stages. Okay, that's a world record. And in fact, and you can see the tip speed here, in fact, the GE90 core compressor is essentially, when GE decided to design the GE90 in the early 90s, actually, they went back to this and they scaled up this design. And so essentially, the GE90 has a compressor ratio on the high pressure compressor ratio of 23 in 10 stages, and I still believe that is a record, and it has pretty decent stall margin. So over a 25-year span, you see a decreasing aspect ratio. I don't know if you can tell. You can here. I think the next slide shows a better picture of it, but you can see that the aspect ratio of these blades is relatively high here, relatively low here, relatively low solidity here, meaning that light could pass through here, relatively high solidity as you go down here, and of course a decreasing number of stages. And this will show you, here's the J79, which is essentially that same as the CJ805. So late 50s, like late 70s, early 80s, you can see the difference, and note the change in aspect ratio of a lot of these blades. That you should be able to look, you look at these are fairly high aspect ratio, these are pretty low aspect ratio, okay? Stage loading has increased because of higher U-tip, lower aspect ratio, and higher solidity, okay? So what that means is they're able to get higher pressure ratios per stage because mechanically they've been able to increase the tip speed, and these things here allow for better stall resistance. We'll talk about that later. Here's a 1950 to maybe 1990 spool pressure ratio. You can see the trend. It's pretty much flattened out now. Here's an example of a catastrophic failure. So this is the stator casing for an engine where they had a huge stall. You can see that it can be quite violent. Essentially, they call this corn cobbing the stator rows here. This is Inconel steel, by the way, so it gives you an idea of some of the force. Here's some of the blades and destroyed. Okay, again, what is the objective? Change a specified amount of mass flow from state 2 to 3 with the least amount of loss. So going back to our HS Muller diagram, you know, we want to raise as much pressure as we can with as little entropy increase, okay, which translate into as least amount of temperature increase as you can. There are a couple of non-negotiable items that the compressor designer has to deal with. One is someone's going to tell the designer what the pressure ratio across that compressor spool is going to be, okay, and that's something that they have to hit. So if they say, hey, we need this compressor to produce an overall pressure ratio across it of 12, then he's got to hit that number. The other thing that he's got to deal with is you got this much mass flow, okay? And that usually comes from the cycle data, which comes from the mission analysis. So those things are non-negotiable. So what kind of knobs does he have to twist? What are negotiable? Well, the flow path is negotiable. The number of stages is negotiable. The number of blades and stators, solidity, the aspect ratio, how you choose to align the vector diagrams, which we'll talk about, and of course the blade shape. Okay, so these are the kinds of things that the designer has at his disposal. So we talked about low aspect ratio compressor blades. What is the effect of when you move to low aspect compressor blades? What are some of the effects of doing that on these different parameters? Like durability. Well, they become more rugged. So a shorter, squattier blade becomes more rugged. There's a smaller cantilever. It's more durable. Fewer number of parts. There's fewer stages. Because the low aspect ratio lets me have more stall resistance, I can use fewer stages, and it makes it way less. The efficiency, if you're doing it good, will stay about the same. And of course, the main reason for doing it is that it's better for stall resistance. The aerodynamic effects of low aspect ratio blades can be seen here, where it produces higher Reynolds number, and these are the effects on efficiency and stall resistance. The really bad part in all this is having lower aspect ratio blades results in some thicker wall boundary layers. So you have to be more careful about how you design such that you can minimize those losses. Okay, and then it also means that you're going to have larger twist angles. And by the way, what I mean by twist, that means I'm going to have more of a twist from the hub to the casing, and we'll talk about why that happens. And because of that, you can induce more secondary flows. So a typical flow path, and this is something just to, as a way of when we talk about this, for a compressor, okay, will look like this. It may or may not have what's called an inlet guide vane, an IGV. In fact, most compressors that you see that are in turbofans that are buried after the fan don't have an IGV, okay? I'm going to come back to that, and we'll talk about why you would need something like this. But a typical axial flow compressor system starts with a rotor, okay? So here's all the rotors are they're all connected to the same shaft, so it turns with a rotational speed, omega, and so all the rotors will rotate at the rotational speed, omega, okay? And that's followed by what we call a stator, stationary rotor. It doesn't make much sense, but that's really the origin of that term. So you have a rotor and a stator. The stators don't move relative to a laboratory-based reference system. The rotor is moving relative to that. So the rotor is actually what's putting work into the fluid. Okay, so as the fluid enters into the compressor, these blades and the flow through the blades have a tangential momentum imparted, okay, onto an element of this fluid, okay, and literally just like we did with first principles on jet propulsion, we're changing the momentum of the flow of this working fluid. That must mean there must be a force. The force here is the loading on the actual rotor blade, okay? So you got to think about it as we're changing the angular momentum of the fluid particle that translates into this loading on the blade in the circumferential direction, okay? So the whole job of these rotating blades is to impart a change in angular momentum, and that will result in work equal and opposite onto the fluid, which will raise the pressure. The reason why you need stators is as the flow leaves the rotor, you've added tangential momentum, so you've changed the tangential velocity component, okay? That means that the angle of the flow that would enter into the next rotor row would probably be at an angle of attack that wouldn't be optimal. Maybe it'd be very, very steep to where it probably would stall, okay? So we need to move the flow back to a more reasonable angle of attack, and that's the job of the stator, to guide the flow back to a reasonable angle of attack for the next rotor. Okay, so that's why you have rotor, stator, rotor, all the way to where you exit the combustor, you're going to have a stator. In fact, typically this stator right here is called an OGV, or an outlet guide vane. You know, and it makes sure that the flow that's entering into the combustor is pretty close to axial, or is trying to take some of that tangential velocity out. So let's go back to the IGV. Why would you need an inlet guide vane? Well, this gets back to what this rotating airfoil actually sees. The flow that it sees, it's relative. It's the relative velocity that matters. And you know from just solid body mechanics that the actual velocity that occurs will be a function of radius, right? Omega r will be the velocity. So the velocity near the tip will be higher than the velocity near the hub. It turns out that if you don't want to have very, very high velocities here, in fact, maybe you want to keep it all subsonic, relatively speaking, the relative velocity, then you want to make the relative velocity entering or hitting that rotor lower. Well, one way to do that is to take the velocity that's coming in and give it a direction, give it a push in the direction of rotation. Then the relative velocity on the rotor will be reduced, right? So if you think of it as a vector, and it might become clear when we look at it in the other dimension, this IGV will be canted in the direction of rotation, and it will turn the flow along with the direction of rotation, thus reducing the relative velocity of the rotor, and thus reducing any shock strengths or shocks altogether. The other feature about that, when this was developed in the 50s, so this has been around a very long time, is the concept of variable stators. Okay, so as we talked before, I'm going to go back to this plot. These are stationary blade rows, and we said that they're there to set up the flow to the next series of rotors. Of course, if it's all fixed geometry, it's going to be set up for a particular given condition of mass flow and velocities that come in. Well, as we know, the jet engine operates at a lot of different, or the engine can operate at a lot of different conditions. Certainly when you first start up one of these engines and it just starts turning, the velocity angles of attack, if you will, are way off, okay? And starting one of these axial flow compressors when they first started using them was a very serious problem. And so somebody said, well, if we had the ability to variably change these stators to make them optimum at different conditions, that would be a big help. And so this was born, and this was a pretty slick mechanical device here. So essentially, these stators through a spar that goes down through roughly the center, the aerodynamic center of these blades, can be controlled. Their angle can be controlled by these levers on the outside. So you can, if you look closely here, you convince yourself that if I push on this, it'll turn this, it'll change this angle, okay? So at the beginning when I'm starting, I can have the flow guided in such a way that I don't stall in the rotor, and as the speed picks up and it starts to pump more, and I get more mass flow in here, then these can kind of settle back into where their design is supposed to be. Now they're all computer controlled and scheduled. I don't think there is a modern jet engine now that does not have variable stators. It's an extremely useful way to help prevent stall and help efficient starting and help operate at different inlet conditions. Here's another picture of one that's in a laboratory. These are all individually adjusted. Okay, so what I want to start to talk about now is how we go about generating the governing equation of the compressor work for a blade row. Ultimately, what we're going to do is, from the cycle data, create the change in momentum and the angular momentum that we're going to need to produce the pressure ratio that we're looking for. And what we're going to do is we're going to equate an aerodynamic conditions with thermodynamic conditions. What are the aerodynamic conditions of these rotor blades and stator blades that are needed to produce the thermodynamic properties we're looking for? Okay, so I know I'm going to need some change in tangential. What does that mean in terms of the velocity changes? The velocity changes in the tangential direction. The velocity changes in the radial and the axial direction. Okay, primarily it's going to come out to be where we're interested in the tangential velocity. And once we figure out what tangential velocity, meaning the magnitude and the direction, are needed, then build me a blade and an aerodynamic blade that can do that. Okay. So one of the things, the control volume analysis that we're going to use, since it's an annulus, right? If you think about the flow path through there, it's an annular type of a volume. It lends itself very nicely to cylindrical coordinates. Hopefully, at some point you went through, you've done some things with cylindrical coordinates, and that'll be very helpful to in our analysis, because it's kind of set up that way, where we'll have a tangential direction or circumferential direction, theta. Sometimes we'll use U to denote that. The axial direction will be denoted by Z, and of course the radial will use R. Some basics about turbomachinery blading, and again, I'm going to say compressor here, although a lot of this translates to the turbine as well. You have, the earliest compressor blades are simple, what we call circular arc airfoils, where the upper surface was a circular arc of a certain radius of curvature, and you had the pressure surface, and of course you have a mean line, you have a chord, okay? And so you've got to envision the flow, in this case, maybe coming down here. So the axial direction is the vertical from top to bottom. So, and the rotation is from left to right. So as this moves left to right, we've cut this compressor blade at some radius, R, okay? So looking at this picture here, and I assume that you can see this pointer, by the way. The bottom surface we call the hub. The top is the casing, and of course there needs to be a gap here. And so we've got the H is what you would equivalently call the span of the blade. Okay, we've already said what the chord was. The spacing is the linear distance in the circumferential direction from leading edge to leading edge. Okay, So the chord divided by the spacing is something we call sigma, or the solidity. That will have a value at a given r. So in reality, the solidity could be a function of radius if r is in this direction. Okay? The aspect ratio is just h over c. Instead of using angle of attack in turbo machinery, they use incidence angle, which is essentially the difference between the mean line angle and a flow angle. Okay, the flow angle being beta 1 or beta 1 star. Okay, so the incidence angle I is that difference, and that's kind of like an angle of attack. The stagger angle is the physical angle difference between the chord and the axial direction. Okay, it's not defined by an aerodynamic term. It's defined geometrically by the actual chord line in the axial direction. And of course, you have some thickness distribution on this. So in general, this is very simple. You also have what's called a deviation angle, in that you have a difference between the angle at which the flow leaves the rotor versus what it would leave left exactly tangent to that mean surface line. Okay, so in a confined annular space where you have blades, tandem, around the circumference, there can be deviations of it. So if you set it up in the angle between this tangential direction and the mean line is 45 degrees, the air angle may not be that, and the difference will be what's called the deviation angle. Okay, so I'll be repeating this because it's important, and you're going to have to get used to how you move back and forth between the absolute frame of reference and the relative frame of reference, and you connect the two by the rotational speed. So given a blade moving from left to right here, there is a relative air angle on this as it moves. So if you're sitting on the blade, you're sitting on here and you're moving with it, you would see this yellowish velocity vector coming at you. Okay, and so the aerodynamics of this 2D section will respond to that relative velocity angle here, or vector. Okay, but if you're standing in the laboratory or on the ground, away from not on the rotating blade, you would see an absolute velocity vector that would be here. So we're calling this W the relative, and we're calling this C the absolute velocity vector. Okay, and the way they're related is the rotational speed. So at some r, I can say that the rotational speed U is omega r. So U is omega r, whatever r is and whatever omega happens to be. That means that the absolute velocity vector C is the vector addition of the rotational speed U and the relative velocity W. And you will use this fact to move back and forth. If I know W and U, I can find C. If I know C and U, I can find W. Okay? And then, of course, we'll be using geometry and trig with the angles that are made. In your book, this is a fairly handy way of looking at it. If you, they basically unwrap this annular blade space here, and so you're looking at it like it's 2 dimensions, even though it's wrapped around, but it gives you a good visualization. So flow, in this case, is moving from top to bottom. And in this case, they included an IGV. So flow's coming in, absolute velocity C here, and it's just, it has no angle to it, it's just coming straight in. Here is the first rotor, okay, of the first stage, and it's moving from left to right in this direction. Okay, so in this case, we want to create a relative velocity W1 here, that is somewhat lower than it would be if we didn't have the inlet guide vanes. And the way we're going to do that is we're going to kick the flow in the direction of rotation by an amount alpha. So these stationary blades IGVs, we're going to take this flow and put a turn on it by amount alpha. Okay? That is going to produce a relative velocity W1 with an angle beta relative to the axial. Okay? And if you combine this triangle here, these are called velocity triangles, on the same geometric space as you have with the relative, you can identify the absolute angle alpha, absolute velocity C, and the same with the relative W1 and the relative angle beta, and they're connected by the rotational speed W. You can take these W1 and C1, the relative and the absolute, and break them into their tangential component and their axial component. In this case, the tangential component has the subscript U. So WU1 is the relative velocity component in the tangential direction of W1. CU1 is the tangential velocity component of C1. Okay? As it leaves the rotor, it leaves with some beta 2. Okay? And before I go back into rotor 1, I want to be able to bring the flow back to where my beta 3 is close to where my beta 1 was. Okay? So I have similar flows going into these two. I might want to change that. That might change as part of your design. But typically within one stage to the very next stage, the betas are close to each other. So this stator needs to turn the flow back, okay, and produce this, these inlet conditions here. And you can kind of walk your way through that. And again, read this section in the book and get comfortable with it. And working problems is the way to get comfortable with it. So. That will end this lecture for right now. This is the end of lecture 1.